Well, welcome to one and welcome to all. You're here to hear a talk about 3D printing. So I should start off with a sound and vision check. I wonder if those of you who are listening could give me some feedback on the chat. Is the audio coming through okay? Hopefully you're seeing video and audio at this time. Testing, 1, 2, 3, testing. Quick bit of feedback on the chat would be very helpful, thank you. Super, thank you very much, Jim. Excellent, thanks Hugh. Nice to see some feedback. That's great. It's not just me here on my own. Super job. Okay, you've seen what the talk's about. I'd just like to say that the talk today comes from GM6NX Amateur Radio Club. If you're not already a member, why not look us up on the internet? You can find us on gm6nx.com. Or if you're interested in perhaps giving a talk, why not drop us a line at secretary@gm6nx.com. Certainly be very interested to hear from you. Okay, the subject today is design and create using a 3D printer. It's great fun. I'm hoping to get some of that infectious enthusiasm across to some of my fellow hams and anyone else that might happen to be listening. 3D printing's certainly of interest to amateurs because you're able to produce parts for your radio hobby. Parts such as line winders, dipole centers, coil formers, electronics hobby boxes, clamps, large radio tuning knobs and the like. I suggest that you can look at 3D printing as just another useful tool in the toolbox. So I'm hoping that you'll find this talk interesting enough to consider giving it a go. And if you do, I'm happy to help and support where I can. The rewards for creating and printing your own parts can be immensely satisfying. So what I want to do today is take you through the process. And that will be the majority of the time that we spend here, looking at the elements and the components that you need to put in place to actually make your own 3D printed parts. On the way there, I'll start with an intro to give a bit of a starter for 10 on what 3D printing is all about. And towards the end, I'll show some of the parts that I've created and printed myself. I've only been doing this for a couple of months so far, but I'm absolutely delighted with the progress that I've made. So to get us all on the same page, it's important for you to know that I'll be talking mostly about 3D printing for the hobbyist at home. I'll be focusing on the most popular of the technologies, which is FDM or FFF printing, which is fused deposition or filament material. There are other technologies, and I'll be happy to talk about them later if there's any interest. But I'm going to stick with the relatively popular, simplest 3D printers. To give you some idea of timing, I anticipate the talk is going to take about an hour. So hopefully you'll find it interesting enough to stick with me through to what I hope to be some Q&A towards the end. I'm getting some good feedback on the chat, so thanks very much, guys. Right, you'll be aware, how could you not be aware that 3D printing's been in the news recently? It's hard to avoid it. Many hobbyists across the world have been involved in making up for shortfalls in supplying PPE, as well as pieces for some hospital equipment like ventilators. One of the main manufacturers of domestic printers is a company called Prusa. And Prusa has been pivotal in submitting face mask designs into the public authorities around Europe to help get the authorizations and the validations for particular designs. The work that they've done has enabled an army of hobbyists to step up and help supply their local medical facilities with pieces that they weren't able to get. But not only that, but pieces that they would find acceptable. So the picture on the left is clearly some face masks. The picture on the right is ventilator valves. And this became an issue in Italy during the peak of the air crisis, when they discovered, or the world was discovering, the need for oxygenation. And they discovered they were extremely short of equipment. So once again, hobbyists stepped up to the plate and were able to react very fast. On the wider front, I wanted to mention that applications of 3D printers are growing extremely rapidly. This actually goes back to 1983, but I'm not going to go back that far. But far from just being engineering and industrial tools, 3D printers have demonstrated their worth for all sorts of sections of society: artists, surgeons, scientists, educators, and hobbyists. In elective surgery, for example, matching up a 3D printer with the output of medical scanners has enabled surgeons to 3D print human organs in order to plan some challenging operations, an example of which is separating conjoined twins. To highlight a couple more examples, the picture in the screen in the middle is of a Braille calculator. And one of my favorites, the bottom right, is a picture from Oak Ridge National Laboratory. This is the largest lab in the US Department of Energy. And a key project there is to use 3D printing to get the US to a point in 2023 where they're going to be able to 3D print nuclear reactors. Now, you might think this is fantasy land, but Oak Ridge has already demonstrated a prototype which they achieved in a 3-month sprint program. The material being used is stainless steel, using laser printing at 1,400 degrees C. On a space theme, you may not be aware, but astronauts have just restarted flying from American soil on American rockets up to the space station. And part of the deal was in the innovation and redesign that's taken place over the last 9 years, helmets are now 3D printed. So on the left picture there, you'll see a helmet designed by SpaceX, which went up to space for the first time about a week ago. In the center, you will see at the top, the Dragon spacecraft, which is the part of the rocket that the astronauts go in. And you'll see it under test using the abort rockets that are built into the Dragon capsule. Unlike anything that's been done in the States before, the Dragon capsule's got the ability to flee an exploding rocket, and it's been demonstrated to be able to do that. So the rockets that do that are called Super Dracos, and they were amongst the first rockets that were 3D printed. So that's quite awesome technology, because there's quite a lot of stresses and strains and thermal issues to do with that kind of application. And the last picture on the right is the first 3D printer that was used on the International Space Station. 3D printing has become quite a strategic decision for NASA, because they were able to demonstrate that having a 3D printer in space was a great way to get inventory of spares and inventory of tools much reduced. So great savings in weight, launch mass, great savings in cost. So you can see very wide range of applications. So what we're going to cover in the core of the talk, our design walkthrough, the overall process. So the very first part is the design of a 3D model. This, of course, needs CAD software But before you all get too worried, there are many options out there at different levels of complexity and functionality. But the options include many that are both highly functional and free to use. The next stage involves an ability to take the output from a 3D model and translate it into something that a 3D printer can understand. So the bit in the middle is called a slicer software. And again, there are many options for the hobbyist, including many that are adequately functional and free. Note, of course, that one option is not to 3D print the model yourself. You can send it off to an online 3D print shop. And I've actually done this myself. Last year, I was looking for a desktop support for my HF radio. And I downloaded some 3D brackets off the internet, sent them off online to a 3D print shop, and got the brackets back all very quickly and very, very cost effectively. So there's also an option to bypass the design stage. So there's plenty of ways of getting involved in this hobby. So rather than design a model yourself, it's quite possible to download a model off the internet. And I'll go into that a little bit later. So what I'd like to concentrate on now is the makeup of the two files that are important here. So first of all, there's the STL file, which comes out of the CAD system and goes into the slicer. And secondly, there's the G-code file that comes out of the slicer and goes into the 3D printer. So the STL file, and to be honest, it's what it stands for as an acronym is kind of lost in time. There's at least 3 different things it could stand for. But basically, it's a format that describes the surface geometry of a 3D object. And it does that by carving up any 3D object into triangles. So that's sometimes called tessellation. And you can see 3 examples of a sphere in the image here. The only difference being the number of triangles that are used to make up the sphere. So you get increasing accuracy with increasing size of file and storage and all the rest of it. But the basic idea goes back to the 1980s. There's a guy mentioned here called Chuck Hull. Chuck Hull is claimed as the inventor of the 3D printer back in 1983. The STL file was created in 1987. The story about Chuck Hull inventing the printer is really interesting. At the time, he was a designer and responsible for making a lot of prototypes for an injection molding process. So there was a lot of interaction between Chuck as the designer and the injection molding engineer. And to be honest, it was a source of great frustration to Chuck because it could take weeks to get his 3D model accepted by the injection molding engineer. And there was a constant toing and froing, tweaking the design to make it fit in better with the injection molding process. So Chuck was convinced there was a better way, and he came up with what was effectively the world's first resin printer. I'm not going to be talking about resin printers today, but very similar in concept in that they both needed an STL file. So the next file of interest is the G-code file. G-code is basically a series of a low-level series of instructions that are intended for a specific 3D printer. So the slicer software has to have 2 different inputs. It needs to have, first of all, the input of the face description of the 3D model, the STL file. It also needs to know what kind of target printer it's using in order to generate the right G-code. Well, hopefully you're with me so far. I think now is a good time to introduce you to the fact that a 3D printer can be a relatively simple beast. If you take a bunch of stepper motors and you take an extruder, which can be made to heat up and push some filament through it, and a microprocessor and a movable heated bed, then you've got the makings of a printer. So what this G-code is doing is basically providing the XYZ information for the servo, the stepper motors, and it's providing information to the extruder about how fast or slow to push the material through the heated extrusion process. So in terms of the G-code file, if you can think of it as being split into three sections, the first section being setting up the 3D printer to be ready to do the job. The footer or the tail, the bit at the end of the job, is where the 3D printer is instructed to make itself safe, park it in a reasonable place, get all the stepper motors to go to a home position, switch off the heat, switch off the fans, make the printer safe. And the core of the G-code file is just a whole bunch of very detailed commands like this G1 command that's on the screen here. So let's put into practice what we've learned so far about the components that make up a 3D printing process. There's four of them. There's the design software, the slicing software, the 3D printer itself, and the actual filament that you're going to extrude. So I'm hoping you can see this screen reasonably well. I'm going to make it full screen just temporarily, because what I'd like to do is kick off this video. So you should be able to see what a 3D printer looks like in practice. And I'm just going to call out the various parts. Right at the bottom of the 3D printer, you've got the electronics box. You can see there it's got a color screen. It holds the power supply, it holds fans, and it holds a microprocessor board. Above that, you can see a moving bed. It moves in the Y direction only, i.e. front and back, and it's capable of being heated to different temperatures. Above that, you'll see a horizontal beam that's holding the extruder, and that can move in an X direction only, i.e. left and right. It's got a couple of fans mounted on it, and you can see the orange filament coming from the spool at the top and being fed down into the extruder. And the last part is the vertical gantry, which is holding the horizontal beam. And that contains the Z-axis stepper motors. So that's the basic components of the 3D printer. So I hope you're with me so far. What I'd like to do now is move over to some of the software that's capable of making a 3D model and then turning it into something really useful. So hang on to your hats. We're going to get our fingers dirty and go and do some software now. So what I'm going to show you first of all is one of the CAD packages. Now, as I mentioned earlier, there's several possibilities that you can use. I've got a screen coming up later that shows you what some of these are. Bear with me while I just kick this off. Here we go. Right, now this one here is called Fusion 360. Let me just check that's coming up on the screen. Yeah. Now, this is very much a recommended CAD package. It's capable of fantastic stuff, and I'm going to show you some of that. I'm going to show you, for example, a couple of the designs I've done. Here's a mobile phone rest that I've made. Here's a peg that I made to fix a broken one out in the garden. There's all sorts of things I'd like to show you. But what we're going to do just now is just make a piece very quickly, because I want to have a piece that I can then take into the next piece of software, the slicer, to be able to show you the whole process going through. Now, bear in mind that this is not a tutorial on how to use Fusion 360. Quite happy to do that, but we don't have time to do that just now. So please forgive me if some of this seems to rush past a little bit too quickly. But I really like you to understand that getting to this level of skill with Fusion 360 is relatively easy. It'll probably take a couple of days, and that's you. So what we're going to do is, first of all, create what's called a sketch. Now, in Fusion 360, sketches are two-dimensional drawings. And from the two-dimensional drawings, you then make a 3D object. So what we do, first of all, is we choose sketch here. We then have to choose the plane, the XYZ plane that we're going to put our sketch on. And you can do that by choosing one of these yellow planes here, or you can do it by choosing the face on this cube here. So I'm going to choose the top. No, I won't actually, I'll choose the front. Right. So having got a two-dimensional sketch, you'll see that you may have noticed that the menus have changed. Don't worry if you didn't spot that at all. So I'm going to make basically a 3D box very, very quickly. So I'm going to use the rectangle tool. And all I have to do is choose the center of the rectangle and then pull out the box like so. Okay. Now, I'm going to stop there just very quickly and show you that there is a very neat dimensioning tool. So what I can do is just switch to the dimension tool and just put my dimensions in by hand like this. So you can see it's very easy to do something very quickly and then zoom in later to the detail and get it accurately. So I want this to be 100 by 50. So there we go. I've got my two-dimensional sketch. I'm now going to turn that into a 3D object, which I do by extruding. So I'm just going to press the E key, which is the short code for extrusion. You can do all of these via menus, or you can do them by using the shortcuts. So right, I was just about to do an extrusion. Right, so what I'm going to do is I'm going to make this be 20 mils deep. And that's all it takes. So I've now got a 3D box. So I'm just tilting this around so you can see what I've got here. All right. Now I want to make a couple of modifications to this box, again, just to show you how easy it is. So that's done by creating another two-dimensional sketch. So I pick on sketch, I select the face that I want to work on. The application's clever enough to orient it for me. I'm going to choose the line tool now. I don't want a rectangle this time. I want to use a line tool. And I basically just choose the start of the line, the end of the line, carry on to make the next line, bring that down back to the box, and that's me done. I'm going to extrude that as well, just by pressing the E key. Again, don't panic if this is all going too quick, but you can see what I've now got is I've got a three-dimensional object with a two-dimensional plane on it. So I'm going to click the plane. It's going to allow me to extrude this piece, and I'm going to extrude it the depth of the box. So again, another 20 mils, and that's done. I'll make another quick change to this box. So I'm going to make another sketch. Again, I'm going to choose the face I want to work on. I'll choose the line tool again, and I'm going to do something similar to what I've done here on the opposite face. So I'm going to start here. I'm going to come down, and then I'm going to drag. And in dragging, I create a circle or an arc, and then pull into here. Okay, so I've now created another sketch. I've created another two-dimensional part on my three-dimensional object. I'm I think what I'll do is I'll put a circle into this as well. So I'm going to choose the C for circle tool, click the center here, drag that out. I'll use my dimension tool to make it the size that I want to make it. So what will I do? I'll make it 12 mils, let's say, just for a bit of fun. Right, now that's me finished there. I'm going to extrude that piece as well. So I've chosen the extrude tool with the E key. I'm clicking on the face. I want to extrude. And as before, I've got the opportunity to drag it up, drag it down. I'm going to drag this down just 5 mils this time, not all the way to the bottom of the box. So just to see where we've got to, okay, this is what we've got to so far. Two more things I'd like to do to this object and then we'll move on. So what I'd like to do first of all is add some fillets to this box. So I'm going to choose the F key for fillet, and I'm going to choose the edges that I'd like to fillet. So there's 2 edges I've chosen, 3 edges. Let me just move this along a little bit. Now I can't see the 4th edge, but you'll see that I can actually, by putting the mouse over it, it shows up. So I can actually click on it there. So I've now got 4 edges selected. All I've got to do now is choose the size of my fillet, and I'm going to make that what 5 mils. So there you go. I've got my fillet. So that's me finished. Oh no! One other thing I wanted to do. I wanted to make it a hollow box. So let me just show you again. Start another sketch. Choose the face. I'm going to choose the centered rectangle again. It's really easy, this. Choose the center and drag out, so to about there. And now I want to extrude again. Remember how easy this is. So I choose my face and I drag this down. Now remember, we made this a 20 mil box, so I'm going to take this down, let's see, 17 mils. Okay, so there we have our box. All okay so far, I hope. Let me just check and see if I'm getting any bad comments. No, we're all good so far. Right, I know it's going very quick, guys, but bear with me. So what I'm going to do now is I'm going to save this design. I'm going to put it in my amateur radio folder, and I'm going to call it test file. How imaginative is that, eh? Text file, right? Okay. Now, the most important thing I need to do is not just save it as a 3D object. I need to save the STL export. So what I'm doing here, if you remember, is I'm taking a 3D object, I'm splitting it into faces, and I'm just going to describe the surface of that 3D object using triangles. So I'm now going to save this somewhere, hopefully somewhere useful. So if I go to here, right, so that's me saved my STL file. You still with me, guys? Hopefully you are, but we've just 3D designed our first object. Now I can do a couple of things. I tell you what, we'll have a quick light break there. What I'd like to do is go back to that screen and show you some designs that I did yesterday. So the first one I'm going to show you is my mobile phone holder. Now, I don't know if this is going to work, but hopefully you can see my very rough sketch there. I designed a phone holder that was going to save my arms from all the video conferencing I'm doing. Something that would sit in my desk and hold my phone both in landscape and in portrait. So I went into Fusion and I created an object. So let's go back there. So this is the piece that I created, and it was actually great fun to do and relatively simple. So there were some considerations about the design, obviously, but I won't go into that here. It had to be the right kind of angle. It had to be the right kind of height so that it wouldn't topple over. It, of course, had to be personalized. So you can see I managed to do that as well. And it all had to fit exactly my phone. Right, so back to me. So the proof's in the pudding. So here's the printed part. Hopefully that's, you can see that. Hopefully you can just about see the finish too. The finish is absolutely incredible. And so from a practical point of view, this holds my phone for conferencing, and it holds it that way as well. Okay, the next thing I was asked to do by the lady of the house, we've got some solar lights in the garden, and the base of one, the peg that goes into the ground, shattered. So I was asked to design a new one. So I don't know if you've seen any of these before, but it basically looks like a spike that fits inside the solar panel light, and the spike goes into the ground. So this had sheared at the stress point here. So I took some measurements from it. I went into Fusion. And designed this piece. Now this has got quite a bit more interest going on. You can see it's got a disc at the bottom, a disc part way up, and they're not the same. They're not the same diameter. And it's got these blades which start off parallel and then converge on a point. So that's the part that I designed. And then back to the proof in the pudding. So the actual part is here. Hopefully that's picking up okay. Here's the funny bit, guys, because when I showed that to my wife, she said, "That's not right. It's supposed to end in a point." And I said, "Well, I didn't know that. It's not, not like the one you gave me to redesign." Oh well, c'est la vie. Right, now what we're going to do is go across to the slicer application. That's disappeared as well. Bear with me 1 minute. There we are. Right, hopefully that should now be on the screen. Yes, good. Now this is one of several slicers that you could use. This one is from a company called Ultimaker, and it's called Cura. This is an excellent free program which does everything that you need. Now what you're seeing at the moment is in grey. You're seeing the outline of my 3D printer, and what you're seeing in the blue cube there is the volume of the build space that this printer can support. So in my particular case, the printer I'm using is called an Artillery Genius, and the Artillery Genius can support a build volume of 220 by 220 in the XY, by 250 in the Z, or approximately 9 by 9 by 10 inches for the metrically challenged amongst us. So you'll see that up at the top of the screen is where you specify the printer that you're using. I've only put one printer in this because I've only got one printer. The next choice to be made is what type of filament we're going to be using. Now in this particular case, I've got 5 filaments that I've bought myself and put into this model. There's a whole stack of generic options with different types of materials, and there's a whole stack of manufacturers types that are already in the program but can be added very easily. So if I choose PLA orange because it's a nice color, what we'll now do is we'll load up that part that we just designed. So here we are, the well-known TET file. That's interesting. I've obviously designed it in a very unusual orientation. So what you can see is the slicer has brought the object in. What I need to do is to obviously orient it correctly. So let's do that. So what I'm going to do is, this can be a bit of a tricky maneuver, to be honest. When it works, it works. When it doesn't, it doesn't. Bear with me, guys. Bear with me. Here we go. Right. Right. So that's us in the right orientation. So you'll remember the part that we designed earlier, and hopefully it looks very similar to the part that you saw. Okay. And you can see underneath as well, and it's good to be able to do that because you can see it's sitting flat on the bed. It's very important that your model sits flat on the bed. Right. Now, the next thing that's important to be aware is that there's a whole stack of settings that control the final outcome. Now, I don't want you to get too panicked by this. Again, it looks kind of bad. I'm not sure if you can see this. Let me put it on full screen just for a minute so you'll see better. What I've found is that most of the default settings are really helpful, which is good because there is a plethora of settings. What I'm doing at the moment is I'm in basic mode, but there is an advanced mode, there's an expert mode, and there's an all mode. And you end up with hundreds of settings that you can make. But there are some key ones. So the key ones can be got via profiles. So I've got 4 profiles loaded in here. One is low quality, one is standard quality, one is dynamic quality, and one is super quality. So using a profile is a quick way to get out of the complexity of all of these settings. But let me pick out a couple of things just to highlight bring to your notice. The first one is the layer height. The layer height at the moment is set to 0.2 of a millimeter. So what that means is the printer will be building a model using 5 layers to a millimeter. That's pretty fine resolution. And I think some of the objects that you've seen there show you the incredible surface finish that is possible to get. And that's coming from the fact that I'm using 0.2. I can drop that a little bit and I can take it up a lot. Different settings for different purposes. The other things that's important is the temperatures. Now the temperatures are driven from the profile. I'm using a particular filament called PLA, which is polylactic acid. And that's got preferred extrusion temperatures, in this case 200 degrees centigrade, and preferred build plate temperatures, in this case 60 degrees centigrade. Another important thing to bear in mind is the print speed. In this case, the print speed has been set for 50 millimeters per second. And this printer that I have, the print speed can go up to 150, and the travel speed, which is the speed that the extruder can move without extruding, can go up to 250 millimeters per second. So I'm not overdriving this by any manner of means. Okay, cut long story short, we've now got everything in place that we need to be able to do the slice. And it's this big blue button here. Now, when I press the slice, the actual slice job is done very, very quickly. There, it took about 2 seconds. Immediately, you'll get some feedback on various aspects of your model. So, for example, this is showing that the build time is going to be 4.5 hours with the settings that I've chosen. I'm going to be using 35 grams of material, and I'm going to be using best part of 11 meters of filament. Now, just to try and put that in perspective, a typical spool is 330 meters and weighs a kilogram. So it's not going to take an awful lot. And here, based on the prices that I paid for the filament that I've got, this model is going to cost me £1.05 in material terms. Okay, so what we now do is I'm going to click this preview button, and you'll see that what we've done is we've changed our 3D model into a model that's been sliced. So there's quite an important transformation has happened here. We've gone from a 3D object to describing the surface faces to now realigning that as a shape that's based of layers. Now, if you have a look at the top right, the right-hand side of the screen, you'll see a black line that goes from 0 up to 100. What this is telling you is that this model is going to be built using 100 layers. Okay, so let's have a look at that in a bit more detail. If I grab hold of the top of this elevator, I can actually run through the different layers of the box. So you can see that's what layer 1 looks like. That's what layer 38 looks like. That's what layer 77 looks like, and so on. So if I go back down to layer 1, I'd like to show you a little bit more detail of what's going on here by giving you a bit of a close-up. Built into the Cura slicer is a simulation of what the 3D printer is actually going to do. And if I set this off, you can see the 3D print head is started extruding in this blue color. Now, the different colors mean different things in Cura. Blue is it's a kind of blue anyway. The blue is the skirt that's being laid down, and you'll see that that's being laid down outside of the model. It's not touching the model at all. So if I flip this around and try and back off a bit, okay, it's going round the outside of the model. Now what that's doing, the function of that is it's putting down 4 lines to first of all make sure that the material's flowing smoothly. There's no blobbing, there's no gaps in extrusion, and it gives the operator a chance to spot that there's something maybe badly wrong with the setup. So then what happens is the print head forms the outside of the wall, which it's already finished with, and it's now setting down the first part of the base layer. So let me tell you first about the wall. There are different colors showing for the wall, and that's because the outside is finished differently. The print head runs slightly slower in order to give a much better finish. Now, what's happening just now is layer 1 base is being built. With the configuration that I've set up here, we've asked for 4 layers of base. And then what happens is some interesting changes. So let me just wait until layer 1 finishes, and you'll see it's just about to go into layer 2. So now you can see it started in layer 2. So I'm going to finish that. And I'm going to move up to a bit more of an interesting layer. So coming up through the layers, we're at layer 4 there. That's the last of the layers of the base. So as we move up from that, you'll see that something rather strange is happening now. So this is called infill. And you can see that we're not laying down solid material anymore in the middle of the model. What we're laying down is an infill shape. Now, one of the clever things about Cura is that it's got loads of different infill shapes, and you can choose the percentage that you want to infill. So there's engineering trade-offs going on here. Why make a model like this of solid material when you could have the middle of it partly hollow. If you do it that way, then you're using less material, it's costing you less money, and it's probably going to be adequately strong depending on what you want it for. So this particular type of infill shape is called cubic, and it's not, obviously, it's not just a simple up and down XY type, it's a three-dimensional cubic shape. So let's carry on going up the layers again to see what's happening. So we're just about to hit the inside floor of the box. So you can see we're now laying down the layers of the box. Go up a bit higher. Okay, so now we've finished laying down the base of the box. And if I swing this round again, you can see that we're still wasting this back piece here. There's no need for that to be solid. And we're still wasting the wall itself. There's no need for the wall to be solid. Now, there's one last important point I'd like to make here, and that's when we get up to the lug. So there's the lug at the front here. So if I bring that back down to where the lug starts, okay, so the lug is starting at layer 76. You can see the vertical bar on the right says 76. Now, if we swing this around, there's a problem here, because when the print head gets to this part of the model, it's trying to lay down material on top of thin air. So there's a bit of a problem there. So let me explain a bit more if I stop the screen here. Right, okay. So one of the capabilities of a 3D printer is its ability to bridge gaps. But what you just saw there is not going to be possible. But shorter gaps can be bridged quite easily. So what I'm going to show you is one of the calibration pieces that it's advisable to print. Now, this is called a temperature tower. And with any luck, the camera might focus on it. I'm not sure it's going to do that. But basically, oh, there we go. Basically, there's a, it's slipping in and out of focus. Sorry about that, guys. So each of these sections is printed off at a different temperature. And in this particular case, it's going from 220 degrees down to 180 degrees. And the aim is to see how good is your printer and how good is this material at bridging the gaps. So this has actually worked out extremely well. You can see that each of the sections has got a bridge. There are some slightly dodgy parts of the bridge. I'm sorry, you're not going to be able to see this. There are some slightly less defined parts of the bridge than others, but by and large, this is a very successful bridging tower. Now, the gap there is 20 mils, and this is PLA. So I'm going to show you another one now. This is done using PETG. This one failed. Now, this operates over a different temperature range, but nonetheless, the tower was planned to be the same height as this one, with the same number of steps, and clearly it has failed at this particular temperature because everything at temperatures below this one here collapsed into a heap of plastic. So this is very helpful in figuring out what your model might be able to do and might not be able to do. So if we go back to our problem, now what we need to do is somehow support this piece when it's getting 3D printed. Now the way to do that is to select a different part of Cura's setup configuration. Now there's something down here called support, and if we simply tick this box, bearing in mind I'm operating in basic mode, so the options are pretty simple. What this setting is saying is that everywhere an overhang of 45 degrees or greater is experienced, add some support. So with that single change, we're now going to go back and slice again. Okay, the slicing's done. Now, The astute amongst you will have noticed that the build time has gone up a little. The amount of material has gone up a little bit. Not a lot, maybe about, 7% or something. And the cost has gone up as well. So when I now look at the sliced version, you'll see an immediate difference. You'll see that there's this blue material has appeared underneath the lug. Yeah. You'll also notice that in terms of its density, it's actually relatively sparse. What am I doing? What am I doing? There we go. So the whole point about this part of the support structure is that it should be possible to remove that very easily once the 3D part has been printed. And that is, in effect, my experience. Once this has been 3D printed and allowed to cool, a set of long nose pliers or cutters or a Stanley knife or whatever will just take that piece away with hardly any noticeable effects. Okay, good. So I think we've done quite well there. So let's move on. Bear with me. Jump back into my set of slides. So I wanted to show a few more prints of what I've done with the printer. So this is a real world example, as I call it. And this is one of the earliest things that I did. So the good lady indoors, she wanted a solar powered water pump for the back garden. Great idea. So she bought one, popped it in this bowl. And the marketing states that it floats on the surface and makes a pretty fountain. In practice, the wind catches it, it goes to the edge, and it ends the bowl very quickly. So I come up with a face-saving solution very quickly using 3 of her clothes pegs. But that didn't go down too well because she's apparently got good clothes pegs, and I'd used the good ones. So what I did was I decided to come up with a 3D printed solution. And this is it. It's something that's available on the internet, and it's called a Crocs. C-R-O-C-Z. Now, what I'd like to do is to show you one. So here's one here. Now, this is a very interesting device. Okay, it's a crocodile, and you can see it's got movement. Now, this item is an example of something called print-in-place. Now, a print-in-place object is something that has got what looks like assemblies, but it's not assemblies. It's printed as one piece. And the only way it's possible is by being able to take into account the very tight dimensions between the moving parts. And this actually sits on the bed sideways like this and prints in that dimension. It takes a bit of getting used to this printing in layers idea. It allows you to do lots of unusual things. So here's an example of something that looks a bit impossible. Here's a sphere inside a cube. Looks a bit bizarre. You know, how could you possibly make that? Here's another example. This is a bunch of concentric sections out of a sphere. So, you know, how's that going to work? I mean, it's bizarre, isn't it? It's just weird. How about this one? This is called Nautilus Gears. Great fun for kids. Some more print-in-place things. This is a dolphin. Of course, you knew it was a dolphin, didn't you? But isn't that fun? Great bath toy. And it's just printed on the flatbed in this dimension here. Another example, my friend the shark. Okay, but great fun, very tactile. That's another print in place item. While I'm showing you stuff, I'll just show you a couple more items. This one here is a pen holder. Of course it's a pen holder. You all knew it was a pen holder, didn't you? Okay. And this one's in my marble filament, which is quite nice. I made a stamper. I don't know if you can see the detail on that handle. It's absolutely brilliant. The finish on that is just brilliant. Now this was printed in this dimension here, and you can see I've left the support material here. This was necessary because this part of the model here was not supported, so it had to be printed with support material. So this bit just comes out, and because it's a stamper, there was a mating face that's required, which is this one. So if I hold these side on, you can see it's basically the dovetail principle. Now those two parts go together very satisfyingly, nicely tight, like so. So you end up with a stamper like that. Yeah, tudge. Another item I wanted to quickly show you was this hobby box. Got a box here, very similar to the one that we've just been looking at. Again, finish of it is really good, but this one here has got some snap. I don't know what they're called. I suppose Hugh could tell me. Are these rivets? I don't know what these are called, but they're triangular pointy bits. Yeah, and the lid has been made with the complementary faces. So that just snips. That just slips in like this, and then snaps, and it becomes great for keeping hobby stuff in. Fantastic. Okay, so where was I? Okay, so that was basically me taking you through some sample printed outputs. Let me just jump back to see how the comments are going. Don't worry about it, Neil, no worries. Right, we're very nearly getting towards the end, guys. I want to leave some space for Q&A in case there is any particular interest. This is a very quick picture of some of the materials that it's possible to print with. I'm not going to spend a lot of time on it because it's far too detailed, but I just wanted to say that the one that I've been using most is PLA, polylactic acid. It's made from cornstarch, so it's environmentally friendly, if you like. And it ticks most of the boxes in terms of the attributes of what you would want. You want something that's easy to print. You want something that looks good. It will take a fair amount of stress. And the layer adhesion is high. So in other words, it doesn't delaminate, all of which is good stuff. Where it fails is, and again, it's horses for courses. Its heat resistance is not particularly good. So it fails at about 60 degrees. The other thing is it degrades in UV, so it's not particularly suited for use outdoors. But if you paint it or varnish it, and it's a material that takes both of those, it takes primers, it takes glue, it can be sanded. So very versatile product. But there are lots of different types of material. The other one I've tried is the third one down, PETG, which is a tougher material, which has got its own applications. And the thing I'm looking forward to trying is the second last one there, TPU, thermoplastic polyurethane. That's a material that can be 3D printed successfully. It can be squashed, released, and it springs back into its original shape. And there's applications for that kind of material as well. Okay, so there will be those amongst you who are saying, all that design stuff's all very well, Bob, but it's not for me. Does that mean I can't get into 3D printing? Well, the answer is no, that does not mean that, because there are plenty of sites on the internet where you can download models and print them. And I've given just a few here. Thingiverse, for example, is probably the largest, but there's plenty others. And they're a mix of sites. Some of them are entirely free. Some of them are entirely commercial. Some of them are a mix of the both. Some of them are run by fans. Some of them are run by the printer manufacturers. There's loads, oodles and oodles. So to give you an example, this is Thingiverse. So if you have a look on the Thingiverse website, this is a typical front page you'll see. There's a very good search box up at the top of the screen. You can put in, for example, amateur radio, and all sorts of interesting things will pop up there. Or you can look for all sorts of things. There's games, there's puzzles, blah, blah. So on the website side of things, a couple of things to think about. You can download STL files predominantly, especially in the free sites. You will not get access to a 3D object file. So if you're just downloading an STL file, then that will allow you to print the piece exactly as it is. But if you would like to tweak it in any way, maybe customize it, whatever, it's quite difficult reverse engineering an STL file. It's not impossible, but it's quite difficult. So that's where one of the things you gain if you're willing to pay the $5 or the €10 or whatever it is for a model you particularly want to get, because by paying that money, you then usually get access to the 3D object file so that you can do a bit more with it. The other thing to be aware about with these sites is some of them are marketplaces for you. It may be that you've got a great idea for a 3D printable object. You design it, you upload it to one of these sites, and then you sit back and just watch the tenors come in, and the bank account keeps going up. Wouldn't that be great? A new career for you folks. Right, so as I say, just about finished. What I'd like to do is finish off with a short video, which is showing an interesting application for 3D printing, and then we'll go into the Q&A. But just for your information, what I've done is I've got some example links here. If you want to go and read up some more on the internet, there's lots and lots of sources of information. I'm a great fan of YouTube. And if you go on YouTube, there are sites out there, for example, like Maker's Muse, Product Design Online, Arnold Roundtree, Dr. Vax, 3D Print Creator. If you also go to the printer manufacturer sites, or if you go to the filament supplier sites, you'll also find great sources of interest and motivation. Okay, so I'm going to full screen this now, and then I'll come back again for the Q's and A's. But while I was researching what 3D printers are used for, I came across this, and it's pretty darn amazing. So stand by for this. Okay, I'm going to full screen this.
Is officially underway thanks to this industrial-sized soft serve machine. I'm just kidding. You do not want to eat that. Meet the Vulcan 2. This 3D printer was made by a company called Icon. It weighs nearly 2 tons and can churn out an entire house in just 24 hours of print time. I wanted to learn more about this machine and what it could mean for the global housing crisis, so I spoke with Icon's co-founder and chief technology officer, Alex LaRue.
What we've been able to do is create something that you just set up once on a foundation. You hook it up to our Magma system. This is our material delivery system that we built in-house, and then you're off to the races. 3 people can operate the Magma and the Vulcan, so 3 people in total for both machines, and then you're printing a house.
We saw the Vulcan 1 earlier this year in Austin, Texas, where it printed the world's first 3D printed home to be awarded a construction permit. The Vulcan 2 features some significant upgrades, including an app for tablet-based controls, more reliable, consistent, and speedy printing, as well as a secret concrete-based mix called Lavacrete.
When you've seen concrete made and mixed, poured into a form, it's doing what it likes to do. It likes to just flow. What we are asking concrete to do is quite different. We're asking concrete to flow a little bit through a hose, but also stand up, right, once we've extruded it. And getting that to happen every single time is a massive technological challenge that we have so far addressed pretty dang well, but I think there's still some room for improvement.
To prove the usefulness of this new technology and bring it to the people who need it the most, Icon partnered with a nonprofit dedicated to fighting global homelessness called New Story. Together, the companies began construction of the world's first 3D printed community in Mexico. So far, 2 houses have already been printed atop foundations, with finishing by workers from a local nonprofit called Echale.
This Mexico project was about as difficult of a project as you could possibly imagine. It's a seismic zone. It's extremely remote. Power cuts out from time to time. There are safety concerns. In this part of Mexico, it's just not very safe sometimes. You put all that together, and it's just like an enormous challenge, not just from a technology perspective, just operationally.
Icon says they're planning to 3D print a total of 50 houses in Mexico with the Vulcan 2. The community is designed for people living on an average income of less than $3 a day, and residents are set to start moving into their new homes sometime next year. If you're like me, you might be wondering when you will be able to buy yourself a 3D printed home and how much that might cost. But Icon isn't ready to release all that information quite yet.
The big goal is downloading and printing a home in 24 hours for half the cost, 50%. That's kind of the overarching goal here at Icon. We're not quite there yet, but we're making steady progress towards that goal.
Beyond the obvious terrestrial need for more affordable housing, Icon is also one of a handful of companies currently in talks with NASA about potentially designing 3D printers to build structures on the moon and Mars. Have you seen any emerging technology you'd like to see featured on What the Future? Let us know down in the comments. As always, thanks so much for watching. I'm your host, Jesse Orrell. See you in 2020 with the fam. The world...
Okay, guys, what do you think? That was pretty impressive, wasn't it? Pretty darn amazing. So we're at that stage where we're out of time. I really appreciate the interest that you've shown in this. There's lots of folks on the comment stream here. So what I'd like to do now is just take any questions. I'll just have a look through the chat, but if any crop up, feel free to add them to the chat. I'll maybe take 5 minutes or so going through the questions. So Neil, yeah, thanks very much. Fusion 360 is free, but it's free on an educational and or hobby license. It's not free for use on a commercial scale. In fact, there are some people out there that are slightly nervous about using the Fusion product because all you're getting when you sign up is a 12-month deal. And therefore, Autodesk has the ability to change that model at the end of 12 months. But so far, it's one of the better ones out there. There are loads of options, though. Certainly, I could mention a few if anybody's interested. Is there any more questions? You've used the Cura before, Neil. Nice one. Top quality finish, absolutely. I'm absolutely amazed by the finish there. Okay, folks, I think we're all happy at the moment. I'd just like to finish off by saying thank you very much for your interest. and maybe to remind everybody that we've got another talk coming up in the near future. That's just a couple of days' time. That's looking like a really interesting talk. And should there be any more interest in 3D printing that anybody would like to follow up, I'm sure you can find a way to get in touch with me. Okay, everybody, thank you very much indeed for your time. And let's look forward to the next talk. Thanks, everybody. Stay safe. Oh, hi, Jonathan. I don't know if you're still there. You're asking about costs. It's easy to answer that one. How much is a car? So it's horses for courses. It is possible to buy them relatively cheap. My total budget to get me where I am has been £300. So there's a good way to start. You can pay a lot more. And I think most people would say that you're looking at £500 to £900, that sort of range. But I'm very happy with the artillery products. Good quality build. If you want a larger build volume, it's got a big brother called the Artillery Sidewinder X1. There's other products. There's something called the Sovol SV01, which to me looks like fantastic value for money and gives great finish as well. But there are plenty well-established printers out there that will cost you more. Okay, thanks again. Cheers all.